Hello. What about now? What about now? And now? Slag. Yeah, does it sound okay? What do you think? Oh, well, no, no, no. Okay, where's the signal going? And it goes to Zoom, then to YouTube. I see. Got it. Okay. Very funny. Okay, great. I'll keep mine on. Right. I'll hide. Right. So it's very creative fun. So look this. Yeah. First met him actually in 2010. He did the very some various topics, which was so that was my first time meeting Vikram. Soon after, we went back to University of Melbourne. We'll make predictions about the timing and value measurements, and that's committed to public hearing in science. And we're very lucky to we're in the very central in developing the GSA concept and array. We also work together on developing the GSA projects and joined the faculty in these are not the main things here investigation. This is very broad, the range from objects to matter, and along the way, but Vikram does not develop instrumentation for today. If the cluster already exists, we can solve the problem. We can very often doesn't exist, and itself. And the DSA is the leading point of that Vikram is going to work here. Making that all happen, and I'll he's going to make township and support the Geelong Cats. Finally remember that. Thanks, Greg. Thanks all for coming out as well. Great to see you all here, and looking forward to saying a little bit about what I've done with an amazing group of students, postdocs, staff, everyone at OVRO as well over the last few years. So this talk is somewhat, to some people's amusement, titled Fast Radio Bursts, and that's it. It's mainly because it took me a bit of time to think about what to actually talk about today within Fast Radio Bursts. In reviewing what we've done for this talk, there's just so much breadth in what this group has been able to do that it took me a bit of time really until today to kind of zoom in on exactly what I wanted to talk about, but I hope to present you with a coherent picture. I will unfortunately not be talking about all the other stuff that my group has worked on. We've worked on various topics in black hole astrophysics, in neutron stars, in the interstellar medium, mainly the warm ionized component, instrumentation development of various kinds, and of course, preparing for science with the upcoming DSA 2000 array. At this point, I should also really, thank the students and postdocs who've worked with me over the last few years. This is incomplete. I could only fit so many on the page, but I really want to highlight the contribution of all students and postdocs who've worked with me these last few years. It's been amazing working with all of you. So to start off, I think when I gave a colloquium here towards the end of 2016, which is the last time I've given a colloquium in this room, the main feedback that I got from Shri at the end was, I really enjoyed that great picture that you had at the start of your colloquium. It was nice to sort of sit back and look at it. That was good feedback, so here's another great picture. So what I wanted to do is start off by motivating radio astronomy. Now, I know I don't have to do this to many of you, but it's sometimes good to remind ourselves of why we do some of the things we do, why it's interesting. So this is, of course, an image in the IR from 2MASS. It's a region about a degree away from the galactic center, as you might tell by the very red color of the stars, even in true mass, together with the several dark clouds. My ISM class should now know that some of them are infrared dark clouds and some are other kinds of dark clouds. But anyway, the point is that when you look at this sky with radio eyes, it looks entirely different. This is exactly the same patch of sky, now imaged at 1.4 gigahertz with Meerkat. And the idea is that you now see a completely different universe. This, of course, is just one way that radio telescopes see a different universe. In this case, we're targeting the high energy component. This is every bit of this synchrotron emission from relativistic electrons accelerated in various ways. Of course, you might observe with spectral line capabilities and see neutral hydrogen, for example. But in this case, you're observing a range of relativistic phenomena. The remnants of old supernovae, you're observing distant AGN seen through the Milky Way. You're also observing a pulsar wind nebula over here. You're seeing the diffuse synchrotron background corresponding to the sort of bulk cosmic ray electron population within the Milky Way. And of course, you also see these beautiful non-thermal filaments, these sort of rather thin structures that are observed specifically towards the galactic center region of the Milky Way that remain somewhat mysterious as to what kind of process they represent, exactly where the particles are accelerated, and what sort of drives whatever, potentially a shock or something else that's causing this acceleration. Radio astronomy is amazing and offers an immense potential for discovery. And this, of course, is why here at Caltech, we're pursuing the DSA 2000 project going forward. I'm not going to talk about DSA 2000 at all, except to say that you should all be very excited. It's going to be absolutely amazing. It's going to be the most powerful radio telescope yet built, mainly because of the amazing combination of both sensitivity in comparison to other current or planned telescopes, as well as its ability to survey the sky really, really fast. It allows us to see more of the sky deeper and more often than other telescopes. I'm not going to talk about the DSA 2000, but kind of in the spirit of, how it is that large projects are developed. I really want to highlight this point that technological innovations often lead to some of the most amazing breakthroughs in astronomy. And this is something that I think this audience in particular should be immensely familiar with. Technological innovations are behind some of the biggest discoveries we've made. And I don't mean just sort of physical technology that we build in the lab, but also breakthroughs in algorithms, computing, and so on. Two projects that I want to highlight here are, of course, the very first large-scale blind infrared survey. If you've ever seen an IRC source in the course of your research, you should know that those originated from this particular telescope in Mount Wilson. And on this side, of course, Caltech played a central role in the development of SIS mixers for astronomy, which, among many, many, many other things, led directly to the ability to do millimeter wave interferometry on very long baselines. Today in radio astronomy, there are really two breakthroughs that are driving development, both of which are really being pushed here at Caltech. The first is amazingly high throughput computing and stream processing, whether it's in these field programmable gate arrays, FPGAs, whether it's on CPUs or GPUs, whatever your platform, industry is driving us to amazingly high both throughputs and parallelization of your processing. We're all well aware of this. What we're somewhat less aware of, I think, what's not quite as widely known, is the amazing developments in low-cost ambient temperature receivers, signal transport with high performance. And I'm glad Sandy is here as well. Sandy Weinereb and his group have really pioneered this here at Caltech over the last decade as well. The fact that we can now build receivers that operate at ambient temperature with the same performance as cryogenically cooled receivers is absolutely amazing and is what enables a lot of these instruments we're building. So one of the discoveries, one of the sort of highlights really of radio astronomy in the past decade or so that's kind of been driven by these technological innovations is the discovery of fast radio bursts. This is not a fast radio burst quite yet, but this is the kind of data that we see them in. This is time on the x-axis, frequency on the y-axis, and so we have a time series. We have a time series of 331 spectra. We have a time series of spectra, in this case, sampled at 64 microseconds, so really, really fast. And I'm going to play this through, and a fast radio burst will appear. Of course, you need the sampling in order to observe this sweep of the pulse from high to low frequencies. This sweep we interpret as dispersion in plasma between us and the source. The free electron content defines a dispersion relation that causes a quadratic delay in the pulse with frequency. And so if you work out how much delay you observe and try and relate it to the amount of matter between us and the source, fast radio bursts, at least, they're defined by the fact that there's much more matter implied by this than there is within the Milky Way. These, from the earliest discovery of FRBs, were known to be extragalactic sources by this argument. The distance scale, which turns out to be correct, is that the typical delays of order a second or so give you sort of distances that are sort of on cosmologically significant scales of gigaparsecs. And this is now proven with the accurate localization of radio bursts to host galaxies. Where does the dispersion come from? Well, there's a whole range of things that could cause dispersion along the way. The first and most immediate being the Milky Way. The Milky Way's warm ionized medium and hot ionized medium both contribute. The local group will contribute something as well. The IgM and potentially some intervening structures will also contribute, typically in a dominant fashion. And finally, you might have some host galaxy contribution as well. And part of the challenge with working with FRBs and interpreting the observations is in disentangling these different contributions. But through this talk, I hope to show you that we actually can do this. So from the earliest days, and certainly from when we were planning projects like the DSA 110 here at Caltech, it's been obvious that there were two important questions. One being, what are these things, right? What are the sources of FRBs? Where do these immensely bright 10 to the 39 erg bursts come from? What are the kinds of amazing sources that have the capability to rarely emit such short duration, sort of millisecond timescale events? But also this idea that as FRBs propagate through these different systems along their lines of sight, what actually causes the dispersion we observe? And this is a simulation here that Liam Connor, my former postdoc, made, moving an FRB through a slice in the illustrious TNG simulation, showing that how dispersion measure might be accrued as you pass through, in this case, a large galaxy cluster. Something like 80% of baryons in the universe are not observed within galaxies in the nearby universe. In other words, they're not stars or cool or cold gas. They're instead hot gas, potentially in halos, potentially in group and cluster halos, and potentially in the IgM. We want to know how this matter is distributed, and of course, the big question of how galaxies form out of this matter and then influence their surroundings as well. And so I'm going to work through these questions in turn, starting with the first one, and try and highlight a bit of what we've found here along these lines. So to start with, before you know almost anything else about an FRB other than the radiation you've received when you detect the burst, you can make some interesting and important physical inferences. So when I show an FRB, you typically don't show it with that dispersion sweep. You kind of collapse it back, integrate up in frequency to end up with what we call a de-dispersed time series. In this case, this burst has an intrinsic duration in the source frame of something like a millisecond. And you can also see now that this particular case, which is common to many FRBs, has significant polarization in the pulse as well. These pulses, in some cases, can be 100% polarized. In many cases, 100% linear. In some cases, a combination of linear and circular. But of course, you see everything you want to see. Some of them are also not polarized. So a few things can be inferred from such data. The energy scale can be inferred if you take an estimate of the distance from the dispersion measure. The time scale is known clearly. And once you have a distance scale and an observed rate, you can try and estimate a volumetric rate, and that turns out to be fairly high, in excess of the supernova rate, for example. And then, when you think a bit more, the field rapidly came to the consensus that FRBs have a neutron-star origin. The fact that the rates are so high that several sources repeat suggests non-cataclysmic events. Things start sort of exploding and producing one burst in their lifetimes. And then when you look at the fact that you're ending up with the energy release within a short time scale, that implies a length scale for the source, in turn gives you an energy density and equipartition field strength, and that points to a neutron-star origin. Beyond this, there's also the fact that the radiation actually escapes. And there are various issues to do with bringing the radio waves out of a dense region that neutron stars circumvent. And finally, of course, as I mentioned, the rate and repetition of some sources tells you these are not sort of one-off explosions. These are implied to be persistently existing sources. Now, this is speculation in some ways. What's not speculation is the fact that we do actually have a galactic FRB from a magnetar, which is a very highly magnetized neutron star. This is an amazing discovery to be part of, where with a radio receiver about sort of this big, my former student Chris Pachenik was actually able to detect a radio burst from within the Milky Way that had the same energetics as extragalactic FRBs. For those familiar with Jansky's sort of unit, this thing was 1.5 mega Janskys at 1.4 gigahertz. Incredibly bright. It was first detected by the CHIME telescope in Canada, but way off axis. And so it was difficult to actually know how bright it was until we looked at our data, also found it and measured its brightness. It was coincident with a hard X-ray burst. This thing's also got several fainter bursts. But the basic fact remains that, at least in this case, we know that a magnetar emitted an FRB-like burst. We know it's possible, in other words. And so, of course, the field dived into the idea that, all FRBs made by magnetars. I don't think we have a strong reason against that at the moment, but I do want to highlight some interesting ideas around magnetar formation in the Milky Way that might be intriguing to some of you anyway. So magnetars, of course, when we plot them in this period derivative diagram of neutron stars, they live up on the top right. They're the most magnetized systems. They tend to have among the longest periods as well. And their emission is powered by decay of the magnetic field, not by rotation. The properties of magnetars that we observe are governed by the unstable fields. Their fields are 10 to the 14 Gauss or greater. So the first point to make is that there was a mystery around the observed scale height of magnetars within the Milky Way above the galactic plane. Magnetars tend to be amazingly clustered towards the galactic plane, whereas the inferred supernova progenitors, so OB stars, have a somewhat higher scale height, and pulsars themselves have even higher scale heights. Why is it that the magnetar progenitors tend to be more crossed towards the plane than the broader OB star population remains an interesting question. The magnetar birth rate is also very high, given that these sources are typically quite young. How is it that so many supernovae or some class of supernovae produce magnetars? Nonetheless, something like, despite something like half the number of magnetars having supernova remnant associations, only one of them is in binary. This is work led by Miles Sherman, sitting back there. This is interesting with regards to population synthesis models for the numbers of binary systems expected, as well as the numbers that have potentially got runaway or walk-away companions, and potentially favors the idea that magnetars are preferentially formed by stellar merger remnants. Anyway, all this to say that there are significant mysteries around the formation of magnetars even within the Milky Way. At extragalactic distances, if we assume that FRBs are made by magnetars, the problem gets much worse. Because when you look at these things in detail available with very long baseline interferometry, DLBI, and you actually localize FRBs to positions like this little X over there within a star-forming dwarf galaxy, in this case, the outskirts of a Milky Way-like galaxy, and in this case, a globular cluster of M81, we're seeing these sources from a vast range of environments. There's no one typical environment for FRBs. I just want to highlight the fact that these are the localization uncertainties, in this case, this little circle there, that circle, and that cross. We know very well that FRBs come from a diversity of environments. The same is true of the burst properties as well. Some FRBs repeat, some do not. Some look like just impulses. Some have amazing structures within the bursts. Some have periodic activity windows, and that they show up typically every 16 days. Some do not. Some repeat very fast. Some barely repeat at all. You see pretty much anything you want to see, as I mentioned before. There was this idea that characteristically, FRBs tended to kind of decay to lower frequencies even after taking out dispersion. But my graduate student Jacob Faber looked at some data in detail and showed that no, some of them go the other way, like this one in particular there. I'm not sure it shows up on this screen, but that's also true, I believe, of this burst as well. So it's a mess, in other words, right? It's a complete mess. And if we want to make progress here, it is true that we can make a lot of progress with very, very large FRB samples. The same, of course, is true of pulsars, right? By simply observing pulsars and placing them on the PP dot diagram, you know a lot about the neutron star population. But to really get at the basic questions surrounding the sources, we, of course, need to localize them. It was, of course, for example, a localization of a pulsar to a supernova remnant, for example, the crab, that tells us that, yes, this thing really is the collapsed remnant of a supernova, a neutron star. Most open questions require at least the localization of FRBs for individual galaxies. And this is also true, and potentially even more the case, for the use of FRBs as probes of the matter between us and the sources. And so this is what we set out to do on a large scale here in our group. So FRB discovery is routine now. Several thousands are known. These things sort of pop off something like 10 to the 5 times every day. Roughly once a second, somewhere in the sky, there is an observable FRB. But simultaneous FRB discovery and localization requires a kind of challenging combination of technical capabilities. You need your wide field of view to see enough sky to detect them. You need high time resolution to see them and spectral resolution to get rid of the dispersion. And you need angular resolution. A good analogy is actually the human eye. The human eye provides almost all the capabilities of the CHIME telescope in Canada in its field of view, in time resolution, but in angular resolution as well, but not quite in spectral resolution. So I don't actually know the spectral resolution of the human eye. It might be enough. Yeah, check that. Anyway, but that gives you an idea of what we're trying to build. We're trying to build a radio eye, in other words, right? Except with wavelengths that are not hundreds of nanometers, but are tens of centimeters. That's the challenge that we face. So we do this at the Owens Valley Radio Observatory. Now, for another audience, I would sort of highlight all the various projects happening at OVO. I just wanted to highlight this movie, which is awesome, and you should all watch it. I strongly recommend it. I still think it's the best movie ever shot at OVO. Anyways, but yes, OVO is an absolutely amazing facility for the development of new radio telescopes. And the telescope we've been building these last few years has been the DSA 110. The DSA consists of antennas spread all around the site, together with a compact, coherently combined core of antennas on the T-shaped infrastructure used for the millimeter array. The idea is that the core is searching for FRBs in real time. When it finds something, it causes the entire array to dump data to disk, which we then reprocess much like a VLBI system. We sort of play it back again and again in order to process it correctly, to sort of get higher signal to noise, to localize, to measure polarization properties, and so on. And so it's a computing challenge. We have to detect in real time amidst the various sort of interference that we observe, and we then have to sort of reliably trigger storage from that as well. A huge team has worked on the DSA 110. I just want to acknowledge the sort of immense work that this team has put together to build what I believe is the largest array of dishes in the world today, the largest coherently combined array of dishes worldwide. It's been a real journey to try and build this thing. We've had students work in it from the very first dish. I like this picture here because Corey Posner spent I think 4 months in this basement room, day after day after day, splicing 486 fibers in that room. The staff worked on building these things through COVID. In some cases under conditions where we had one staff member per building on site. They could interact outdoors, but not indoors. In the summer of 2020, of course, fires were a big deal as well. And so smoke was rather bad on site as well. To do the outriggers, they worked in amazing heat. They worked through the summer, I think starting at 6 a.m. to 10 a.m. and then in the evenings, again, to avoid the heat of the day, to dig a trench around the entire border of the site, build a road, and place the antennas. Yes, it's been a amazing effort by the team to put together this array on site. I really want to highlight the role of the receivers here as well. These uncooled, highly performing receivers that actually enabled us to beat the spec of sensitivity per dish by 45% over what we promised the NSF. It's amazing when your telescope actually performs way better than you planned, not worse. Again, thanks to Sandy and his group. One thing I want to highlight here is when you put sort of the leading FRB search instruments on a plot like this, which is the sensitivity on this axis and field of view on this axis, where these dashed lines show roughly constant lines of constant detection rate, you sort of find that the DSA 110 appears to be at a bit of a disadvantage relative to some other instruments, like certainly CHIME over there, ASCAP, which is a few $100 million array in Australia that surveys more of the sky with more sensitivity than we do. Meerkat, which is rather similar, but again, similarly sort of well-resourced VLA collecting area in South Africa. FAST, of course, the biggest aperture in the world. We're somewhat at a disadvantage there. I mean, to even get close on a budget that is sort of a factor of several tens lower than these other instruments is remarkable. But the other thing I want to highlight here, given the fact that we are the leading instrument for the simultaneous discovery and localization of FRBs, is this point about pipeline efficiencies. We put a lot of effort into developing a very efficient and performant analysis pipeline that allows us to just not miss events. And that turns out to be really crucial in this game as well, making absolutely sure that you're not actually missing these sort of milliseconds of emission that you might see every week, right? You're staring at noise for a week and you might detect something for a millisecond. That's the kind of challenge that we face in keeping this thing up and running. So what do we know about FRB sources? Well, there's a whole series of papers that I encourage you to look up on our website, led by various members of the team. I just want to highlight a couple of points here and then move on to the next part of the talk. The first is by looking at the actual bursts themselves. This is the compilation of some of our bursts, showing the time frequency data after removing dispersion. Again, you see a whole range of different features, polarization properties, shapes, spectra, etc. But one thing you can glean from this is by analyzing the polarization of the bursts, you can measure the Faraday rotation within the burst, which gives you an insight into the line of sight magnetic field between us and the source. And by a few different arguments, we're able to show that essentially all the Faraday rotation we observe likely originates within the burst host galaxies themselves. For example, we see that the rotation measure and the dispersion measure of the host galaxies appear correlated. We see evidence for redshift suppression of the observed rotation measures. And we're able to then divide the rotation measure by the dispersion measure to get an estimate of the field itself within the host galaxies. And we find that the typical field strengths are somewhat in excess of what you might expect for the Milky Way, for a typical sightline through the Milky Way. This adds to the body of evidence that we're seeing FRBs from a population that is broadly consistent with young stars. So from regions within their hosts where you might find the youngest stars within the hosts as well. So the hosts themselves are varied in many ways. These are 36 hosts ordered by their extragalactic dispersion measure. And you can see, some are nearby and big, some in these pan-stars data are invisible. That's all well and good. But graduate student Kriti Sharma led a work that was published late last year, where we looked at a magnitude complete sample of hosts in exhaustive detail, I think it's fair to say. And we're able to make some interesting inferences. One being that typically FRBs, which here is this sort of black curve in this cumulative plot of the stellar masses of the hosts, generally occupy fairly massive host galaxies relative to many classes of astronomical transient, but are typically consistent with where you might see core collapse and type 1a supernovae, and generally speaking, trace the selection of galaxies by their star formation rate, with a deficit at low masses that we believe is real. The offsets of the host, of the bursts within their hosts, so how far the bursts are from the sort of center of light of the hosts, appears to be sort of fairly low, but again, consistent with supernovae, for example. That deficit, we believe, is it's confusing to put it mildly. The fact that we don't see as many tiny hosts as a comparable supernova sample might contain. Why is it that we're missing low mass hosts? This is sort of exactly the opposite case to what we see, for example, in some supernovae and long GRBs, where you favor low metallicity, low mass hosts. You might interpret this as favoring high metallicity in the hosts, which has where we can make up a story behind that. But broadly speaking, we favor star-forming hosts. This is a caveat to be explained that may have an origin in some of the mysteries about magnetar formation I mentioned before. So what do we actually know about FRB sources now? Well, I think we can synthesize it. I really do think we can synthesize it fairly simply at this moment. First, that the burst properties that we observe are reminiscent of the youngest pulsars. I'm not saying that FRBs are in fact the youngest pulsars. What I am saying is that the FRB emission may well come from a similar region of the magnetospheres of these neutron stars as the emission from the youngest pulsars. In other words, sort of high up in the magnetospheres. The second is that the locations within the host galaxies, as probed by the dispersion measures of the hosts, the Faraday rotations of the hosts, the physical locations in like physical offset within the hosts, and so on, are consistent in every case with typical supernova locations, and potentially, in fact, with this sort of hint of larger host ISM magnetization than a typical sightline through the Milky Way. The host galaxy demographics are largely star-forming, with some interesting caveats, with this general deficit of low-mass hosts, a few red and dead systems, and the rare class of dwarf galaxy hosts seeming to have the highest local dispersions as well. There's some interesting caveats around the edges, but broadly speaking, these are star-forming hosts. And together, I think it's very clear that the dominant channel of FRB source formation is likely to be core collapse supernovae, with some interesting implications based on these, for example, this deficit of low mass hosts around the specific core collapse supernovae that we're looking at here. So I think this is where we are at the moment in our understanding of what makes FRB sources, at least. So, on to the second topic. Again, how do we use FRBs to reveal unseen baryons? So this bit is a kind of a sharp left turn. It's a change of gears. And so let me spend a minute motivating it with some history, and then we'll get to the results here. So, of course, we're all familiar with the sort of basic paradigm of structure formation and galaxy formation in the universe, that galaxies form within a scaffold of dark matter that evolves under gravity, and that the energy density of the universe is split amongst various components, with stars forming a very tiny and minor component of the cosmic energy density, with gas forming a major component of the baryons, dark matter dominating the total matter budget, with dark energy dominating the total cosmic energy density. We also see that galaxies only trace the sort of nodes of the cosmic web, whereas gas kind of exists everywhere with different temperatures, column densities, and so on. Galaxies, as they form, affect the gaseous structures around them via feedback mechanisms. And over cosmic time, the IGM, the matter sort of in between galaxies, rapidly heats up to temperatures in excess of 10 to the 6 Kelvin today, with sort of trace amounts of 10 to the 4 Kelvin gas in the IGM. The same is not the case within the halos of galaxies. So baryon inventories, so trying to figure out where all the baryons are, not just are they in stars and something else, but specifically, let's go line by line, right? What are the fractions of the baryon budget within different components? They've generally come up short of cosmologically inferred values of omega baryon. The sort of classic Fukugita-Hogan-Peebles result from 1998 got about half of omega baryon, and they based on fairly optimistic arguments, suggested that maybe omega baryon is half of the cosmological value, and that something might have happened over time. Later on, Mike Shaw, in a very well-known paper, found more baryons in the IGN, mainly in these sort of weakly sort of observed Lyman alpha systems of low redshift, as well as potentially a warm-hot intergalactic medium observed in quite strong oxygen 6 absorbers, with still some fraction of the baryon budget missing. And Mike and collaborators pointed to, let's use better UV spectrographs and X-ray spectrographs to try and get at lower and lower column densities in this gas. So with FRBs, we argue that we have a unique probe of all the gas along the line of sight. So what we find is, of course, you can compare FRBs most readily to, for example, the Sunyaev-Zeldovich effect, in this case, the thermal Sunyaev-Zeldovich effect, as well as free X-ray emission. In both cases, you have terms in the integral of the electron density that cause a certain weighting of the observable towards certain baryons. You have a weighting of any squared for free emission. You have the weighting by the electron temperature for the SV effect. With FRB, the dispersion measures simply trace the integrated electron column density, and Faraday rotation measures weight the electron density by the local parallel magnetic field as well. So FRBs really offer this unique, unbiased probe of all matter, ionized matter along the lines of sight. Of course, the vast majority of the universe is ionized today. And so what we've done here is basically analyze this relation of the extragalactic dispersion measure with redshift and interpret the observed distribution in terms of parameters of the gas along the line of sight. So the first thing is that the mean DM at a given redshift carries a lot of information in itself, right? In its integral, which now is in a full cosmological context, you have cosmological parameters like H naught, omega m, omega lambda. You also have things like the electron fraction in the gas. You have the fraction of diffuse gas that you observe. And so you're able to get at both cosmology and astrophysics with this integral. But with the variance or spread in the relation in this really amazing compilation by Krithi here, you can kind of see that the spread that you expect in this DM redshift and Macquart relation also carries significant information. And this is depicted pictorially here, where this shows sort of a sort of flyby of structures within 3 different cosmological simulation runs with the same underlying dark matter framework, where you see cases with low, medium, and high feedback of galaxies into their surrounding baryons. You can see that with low feedback, you end up with this sort of rather more sort of clustered structure than with sort of high feedback case, where you kind of wash out structure a little bit. And in those cases, you can kind of translate that into what you observe in this spread in this Macquart relation, the DM redshift relation, to show that the spread in this relation directly traces the amount of feedback that galaxies impart to their surroundings. This, as it turns out, is also a great tracer of where the baryons are. More feedback means you blow baryons out of halos. Less feedback means they stay within halos. In other words, the spread is also a great tracer of the sort of baryon budgeting. Where are the baryons in the universe? So an initial effort by J.P. McCarter, for whom this relation is named, simply tried to look at the relation between dispersion measure and redshift. In this case, just showing that the dispersion measures are sort of consistent with the omega baryon values. In other words, kind of looking at this straight line fit, the error region was kind of what was is sort of illustrative in this case, based on a single model for halo density profiles. But JP really was the first to show that FRBs, with a sample of 5 in this case, are in fact tracing cosmic baryons. This relation does exist. And this is despite the fact that the observed DMs, dispersion measures, include all these different contributions. The fact that there is a relation means that this IGN and intervening halo components are dominant in the DMs of most FRBs. Around the same time, we'll be getting excited over here as well. And in fact, the FRB we first localized here with the precursor to DSA 110, DSA 10, happened to have a quite a fortuitous alignment where the FRB came from this galaxy, but then this one turned out to be a quasar that George Jagoski kindly also got a spectrum of. We put a slit on that. And we found that in the spectrum of this quasar, we were able to see magnesium-2 absorption both at the FRB host redshift and at the redshift of this intervening galaxy pair as well. Now, this is kind of, it's kind of cute, and it allowed us, you can actually put interesting limits on the amount of ionized hydrogen given the inferred neutral hydrogen column. This sort of, whets your appetite. It's kind of interesting. But what we really wanted to do here was to make very firm statements about this basic problem of where the baryons are. So one of the first things we did along these lines was to look at this very top left FRB here with this rather well-hidden negative extragalactic dispersion measure. Now, that's not possible, of course, but it's negative because our basic model for the Milky Way contribution wasn't quite correct. And so we were able to use that event to put a rather tight constraint on the total baryon mass of the Milky Way halo, which suggested that at least 50% of the baryon sort of budget of the Milky Way, if you assume the cosmological baryon to matter ratio, at least 50% of that is missing. It's not in the Milky Way at all. Not missing in the sense of not found, missing in the sense of not being there at all. This is, not a surprise, but it's still nice to see observationally. When you do the McCart relation analysis with a large sample now of localized FRBs, now this is the sample that is in a paper led by Liam Connor that after a long time of not hearing back from Nature Astronomy for various reasons, kind of went through a month or two ago. We're now able to do the baryon budgeting sort of completely. And we argue that we're doing it completely for the first time. We're able to actually trace all the baryons in the universe with these FRB data. And this is what it looks like, right? Where we're saying that based on FRB DMs, something like 75% of baryons in the universe are in the IGN, where we define the IGN as everything outside R57, to be specific, of halos. Just later why R57, not R100 or R200 or 500 or whatever. 75% of the IGN, about 18% or so in halos, and the remainder locked into stars and cold gas. The inference here was using an illustrious TNG simulation to provide the kind of halo scaffold, but then we fitted for the amount of matter at different locations within the simulation box. This is something that has been sort of predicted for a long time as well. It's going way back to Stanton Ostriker, who predicted that a significant fraction of the baryons in the local universe would in fact be in this hot phase that's difficult to otherwise observe. We do this in a bulk sense. We also do this in a targeted sense where we also, when we sort of analyze sightline by sightline, we start to find interesting structures in some cases that correlate with more dispersion, in this case, two FRBs originating from within two different galaxy clusters. But I think the broad result is the one I want to highlight here. This idea that we find a typically low baryon within halos and a rich IGM. Most baryons, we believe, are in the IGM. This is, again, I would argue, not a large surprise. Simulations kind of generally predict something like this, although they vary in their feedback implementations, therefore have sort of vary around this by 10 to 20% or so. You can also do some fun stuff when you have a data set like this. Like, you can kind of go the other way and ask, first of all, if you take baryons in groups and clusters as probed through X-rays, if you take the stellar mass density of the universe probed through optical observations, IR observations, if you take cold gas as probed by H1 and molecular hydrogen observations, and then take our estimate for the total diffuse baryon content, you can kind of go from the top and press down on the total amount of mass in the CGM, specifically the certain galactic medium of galaxies, and find that it contains a marginal amount of cosmic baryon content. You also go the other way with stars and find that bottom-heavy INFs are disallowed by these data. Bottom-heavy INFs would predict roughly double the amount of stellar mass density, and that's disallowed now by this data. And most fun of all, you actually end up with a fairly nice constraint on the order of 10% on omega B H0. That's early days still in this sort of analysis, but it's at least tantalizing at this point. Again, interpreting this requires you to look at both the mean relation and the spread in the Descartes relation, where here we're now showing the implied relations for different sort of ratios of baryons in the IGN and in halos. You can see that as you put baryons in the more and more into halos, you end up with a wider and wider spread. These are the FRBs that we observe on top of the data. Krithi here is pushing in new and amazing directions to try and extend this analysis to actually fitting for the electron power spectrum in the cosmic electron power spectrum, which sort of carries amazing information both for cosmological analyses by large surveys down to very small angular scales, as well as astrophysics in the actual halo density profiles within the universe. And we think this is a very promising approach in the future, especially because FRBs appear to be sensitive across a whole range of masses and length scales within the universe, in contrast to other sort of leading probes of large-scale structure today. We're very optimistic about this. We have some big dreams, but the not so distant future of FRBs, when instruments like DSEC 2000 and CHORD will be detecting sort of tens of thousands of FRBs and localizing them all. We can do some really fun things like finding extragalactic lensed FRBs, gravitationally lensed events on timescales of both milliseconds to seconds, probing compact objects, as well as months to years probing galaxy scale lenses. Whole lot of amazingly fun science along this path. And so, yeah, I'd like to leave it there. FRBs probe a whole lot of interesting electrodynamics, as well as interesting neutron-star systems across a large fraction of cosmic time. And although we think that FRBs primarily originate from sources formed in core collapse supernovae. The exact sort of subset of supernovae that form FRBs remains an interesting question. With our world-leading sample of localized events, we're able to also now open up this field of using FRBs to detect and probe matter between us and the sources, giving us some of the really the first insights into where baryons are distributed in the universe in a cosmological sense. I'll leave it there. Thank you. So we've got 96 working, 96, and they're 4.65 meters, 4.65 meters across. The exact size is a bit hard to measure because the edges kind of roll off a little bit. The 4.65 is the number we use for a given aperture efficiency. Mm-hmm. We haven't looked for that as yet. We assumed a fiducial model for the evolution and quote these numbers at redshift 0. We don't have yet a sufficient sample, say, above redshift 1, I think, to make a clear comparison between the two. But, there's probably of order. They're mostly up to redshift 1. The typical redshift that we observe is about 0.4 or so. Oh, yeah, it'll go well out. We currently have with DSA 110 5 events or so around redshift 1, like 0.97 up to about 1.5. But we probably need at least double that to say more. Eventually, of course, you want to also observe helium reionization at a little higher redshift as well. So it'll be at the moment a fiducial sort of number for the future of this field is of order 10,000 events, and with that, I don't believe it'll be quite as competitive as Sydney, particularly will be quite as competitive as DESI or I'm actually sort of SphereX's prospects, but it'll start to get close. We're somewhat more optimistic that H naught. Not very long, I don't think. I think with the combination of sort of enhancements in our own detection rate and in that of ASCAP and Meerkat as well, I would expect within 2 years or so to have a significant sample above redshift 1. With DSA 2000, the ultimate redshift we probe depends sensitively on assumptions in luminosity function and its evolution. And it's unclear. Some models which suggest we'll sort of max out at about 4. Other models suggest we'll max out at 10. So, yes. Yeah. So it's not entirely clear. We don't know enough about the luminosity function to be certainty. That's correct. Yes. We actually leave in one of the analyses we do, we leave omega B H naught free floating, and allow it to vary arbitrarily, and don't apply a constraint on or prior on omega b. And at least given a reasonable prior range naught, we are in fact seeing all the baryons. Yeah. Of DSA 110, do you mean? um, ah, excellent. Yeah. So we wouldn't use dishes at all. We would try and we would do our best to build an aperture array and put all the feeds facing up and build as many of them as we can, coherently add them all, have order a 10,000 degree field of view, and without rigors to localize. And this would, for the same cost, get you a far greater detection rate. On the flip side, you wouldn't get these events redshift 1 because you wouldn't have sensitivity. So when we started this project, the only telescope with note that was detecting FRBs was the Parkes dish, right? And so we designed DSA 110 to have the same sensitivity as Parkes, but with 20 times the field of view. That was their original design goal, to get 20 times the detection rate, which roughly speaking we have. Like, let's be fair. So but it sort of depends on the science question of interest. I think we've done really well on the sort of probing intervening matter, because we have this high redshift sample. We trace a range of redshifts. We're able to use Keck for several hours in some cases to get redshifts off individual hosts. But we would have gotten much further, I think, on the science of the FRB sources if we had a much larger sample localized in a very local universe. We're actually doing that now, of course, right? But for good reason. So with William, we're building exactly that array now at Owens Valley to get at the very local. Thank you. What's that?